Hey, hi all to this session on preparing for data science interview questions. I'm Karthik. So I've been working in this data science domain for now close to 7-8 years with experiences in companies like Reckitt Benckiser, Snapdeal, Hike Messenger, and currently I'm running a company called Probito, where we develop R&D driven data science solutions for some really complex problems, particularly faced by various industries. So in this session, we are going to focus on certain fundamental questions and the thought processes you need to sit for an data science interview, and then from there on, we'll make the questions a bit more complex as we move on, and we will try to answer which kind of skill sets people normally look at when you appear for a data science interview in any company. So there are various roles depending on that. The complexity and the variety in the questions might change, but this session will try to cover things in a fundamental level so that it prepares in a very common ground, irrespective of which role you are applying for. You might be able to at least get a perspective of what data science requires as such. Right. So with that note, let's see how we're going to structure the various questions that's going to come up in the session today. Majorly focusing on statistics, data analytics, machine learning, and probability. So these are the four headers under which the questions will come, and I'll discuss the question and how to approach a particular question in a structured approach, right? In a structured manner. And once we understand the problem well, we will see how does that thought process of coming out with the solution really works, right? So all of you know that data science is in booming state. Many openings are coming up in across the globe in various companies, irrespective of which company it is, which particular business it deals with. There is a potential of some applications from data science, right? They have a lot of data, different systems of their businesses generating the data with an enormous amount of volume, velocity, and variety. So with that sort of data asset that every company has now got, they want to now leverage it towards growing the business to the next level. So you have some of the stats here, like this is more than sufficient motivation that getting into data science would definitely land you in some really good professional career. Okay, so let's start with the questions here directly. We'll in the beginning start to focus on some of the fundamental questions, which is more for you to understand what is data science than a particular interviewer asking you that question. For instance, many people wonder what data science is all about, right? Though there are many online sources and blogs which describes data science in a very nutshell, this is what it boils down to, right? A person who is very good in understanding the computer algorithms, a person who understands the statistics and mathematical ideas, and applying these two knowledges from the computer science and mathematics into a particular application, right? A business application where somebody sees a value coming out from the data. So how do you apply that? So that's how kind of data science approaches. So when you combine these two powerful concepts coming in from computer science and mathematics on a real world application, the sort of outcome that comes from particular data science project goes in a direction where people see a return on investment, right? So the people you bring in, the technology you bring in, the ideas you are working on, all of it should kind of give you some return on the investment you have put in. So that's where industries are started to looking at data science. So various subjects which are very important for you to know: statistics, computer science, applied mathematics, and then subjects like linear algebra, calculus, and a few more, right? So fundamentally, from computer science, algorithms and data structures might be very useful. From the mathematics or statistics and things like calculus, linear algebra, matrix factorization, and concepts like that. And from the application, it is more from your experiences from the industry. If you have worked for retail, you know how the business process in retail works, right? So people often also ask, from the technology end, do we need any sort of experiences in Python language, right? Python, or like for example R programming as well. So Python is one of the most looked out for kind of programming skills, particularly when you want to build solutions in data science domain. And with availability of libraries like NumPy, Pandas, Python has now established its ground very strongly in giving a very robust framework for designing data science solutions, right? And in particular, things which it has like list, dictionaries, tuples, and stats are one of its own one of its capabilities, which sets Python in its own league of programming languages suitable for coming out with data science solutions. So there are many more other libraries as well apart from this for building machine learning algorithms, but these are some common libraries that you would normally find people using it. And also with distributions like Anaconda, Python has shown its capabilities even for a production grade solutioning, right? Wherein you make sure that all the dependencies that one particular library has for building a data science solution is all in one place. So quite a popular programming language in the recent kind of happenings. Though R programming is also equally good in terms of producing a quick prototype for most of your modeling tasks, but Python is moving itself into a production grade where things can be deployed after the sort of prototype into a production environment, and it can face the customers from day one. So that sort of capabilities are coming up with Python. Right. So let's talk something a bit more specific with the data, right? So when people are doing any sort of data analysis, they normally face something that we know by the name selection bias, right? So what is actually a selection bias? The fundamental place where you start doing a data analysis is by selecting a representative sample, right? So that's where we normally start doing any analysis. So when you working for a company which has, let's say, 1 billion records in their databases, like 1 billion is like very large number, which represents various customers data, or it might also be depending on which feature you are working on and so on. So if you collect all of those, it might very easily come to 1 billion records, which is nothing but in a structured form number of rows. So with that an enormous amount of volume in the data, any analysis that you take up might have to have a lot of filters, like saying I only want to analyze a particular feature in my products, let's say, right? And I only want my customers from XYZ region, which is, let's say, top 4 region or top 5 regions. So you might put many features or filters like this. But later on, if you would like to do a kind of an analysis which covers most of your customer base, right? There comes the tricky situation of not being able to use the entire volume of 1 billion records. At the same time, you want to do a really good study or analysis based on what data you have. So in statistics, we normally use this idea of doing a kind of a randomized selection, right? So with this randomized selection, we make sure that out of these 1 billion records, we are choosing a small subset, let's say of 1 million, which is a true representation of the entire population, right? But what happens with this is, while we do this 1 million record selection in a randomized way, there are chances that you might have certain bias in the analysis, obviously because you are not using the entire population. So selection bias is this particular sort of a characteristics while you are doing a sampling on a large population of data. Very common example for this is if you want to do a exit poll analysis of particular election, even before the election results are coming up, and you have not chosen a representative sample for doing that exit poll analysis, right? By that I mean you only have asked some questions for a selective few from the particular constituency, and they have an opinion towards one candidate, but that doesn't represent the entire opinion of the population in that constituency. So selection bias is very important to handle, and most of the time people employ things like randomized selection or selection sampling techniques like stratified sampling and so on. So by that you can minimize this selection bias. So these are some very generic questions. So let's start with some sort of statistical questions and also how to deal with different types of data. Okay. So doing any sort of data with a structured information. So structured information, I mean there are many rows and many columns, and it looks more like a tabular data, right? So with such a data in place, there are these two different formats, one saying the long and the wide. So let me show you an example here. You have a record of 2 customers, right? And you store just 2 values, which is the height and the weight. So these are in columns. So with these 2 customers, these height and weight being a separate column is one format, like a long format. Let's say transform this by having only one particular column which will say attribute, right? By that, I will bring in these two columns as one column by calling that as an attribute and put the values in one column. So this sort of format is called the long one. So what really happens is, instead of having two separate columns for two of your attributes, you put both of those into one column. And by doing that, there are a lot of benefits with respect to the task you have in your hand, particularly in data visualization. Certain data visualizations would need you to not put your attributes as a separate column, but rather as the one column which can have the attribute names. So which might then go into building your legends, right? So these kind of techniques are kind of very common formats between like the long and the wide, and very frequently will people like deal with both these data formats, so depending on what task they are doing, particularly when we are building visualization dashboards. Okay, talking a bit more on the data analysis perspective, people like know that in stats, normal distribution kind of is that one like the godfather of the distributions. You have many distributions which normally people try to see if is present in my data or not. But the moment people kind of see normal distribution coming up in any data, things are kind of bit easy to understand. And in typical case, any distribution, any data distribution that you would like to find out given data for analysis, it gives us a lot of characteristics around what the data is about. If I'm, let's say, analyzing the salaries of the employees in my company, right? I might see that there are some employees who are in that, like that thick crust in the center, where majority of the people are sitting with a moderate level of salary ranges. And then there are these sort of extremes on the left and the right. So you are like very commonly people refer whenever you talk about salaries to a bell curve, right? And then they start talking about top 25% of the performers in my company, the bottom 25, and the middle one, which you like are sort of the normal performance. So this sort of bell curve distribution is very commonly understood and as well as used in doing many data analysis. So is the other distributions as well. But normal distribution has its own significance. So when somebody asks you around anything around normal distribution, the first thing you should visualize is the symmetrical bell-shaped curve, right? And the moment you get that bell-shaped curve in your imagination, start thinking of certain properties. Like what is the mean of a normal distribution? What is the standard deviation of a normal distribution? And in particular, a special case of normal distribution, which we call the standard normal distribution. So in that standard normal distribution, we know the mean is exactly 0 all the time, and the standard deviation is exactly 1, right? So there are different places where normal distributions are kind of used. And if you are comfortable with ideas like central limit theorem or the law of large numbers, you might want to relate that as well to normal distribution, particularly the central limit theorem, right? But the idea is a distribution which is symmetrical around the mean. So that's what a normal distribution is. So depending on which variable you are trying to analyze, even a given data set, whether it could be like an employee's salary or your sales for a business of yours, right? Or your number of, let's say, interactions of the customers on your product. So any variable that you define can have a symmetrical bell-shaped distribution, which we normally refer by normal distribution. And the moment we understand that something follows a normal distribution, all these properties of that distribution is like revealed. So that's sort of the importance of doing any analysis around the distribution of data. And normal distribution, like very common one. And in many statistical techniques, in even model building exercises, if you have anything in a normal distribution, many other possibilities of applying certain modeling techniques comes out evidently there. And also there are many other modeling techniques in stats and machine learning where there is a fundamental assumption that things should follow a normal distribution. If it is not following, then the model is wrong. So there are many use cases of knowing what normal distribution is. But in simple terms, it's a symmetrical bell-shaped curve. Right. A/B testing. So quite a popular approach, people particularly who are working with product, right? And what happens is when you are as a company having many features inside a product. For instance, if LinkedIn is a company which has a web page, right? It has a lot of features inside that. You have some jobs portal in LinkedIn. You have places where you can connect to your professionals in the similar industry. You can also read about the posts people are doing in the portal and so on. So there are different places in the website with many features. So what happens is, if LinkedIn as a company is looking for some changes, for instance, changing the entire website's design and aesthetics, or changing one particular feature inside their website, right? So these changes are normally accompanied by sort of a process called A/B testing. So what happens, as an analyst, you might be working with LinkedIn and say, on a fine day, they might come out with a new feature, new design, or new sort of changes in their website. So you as a person would tell, okay, this is my framework for testing this new change by defining a metric. So my metric would be, in simple terms, saying, if I change this website from A to B, is my number of footprints on the website going to go down or not? So this is my metric. And if I successfully establish the fact that after rolling out this new website, my number of customers who are going to visit my website is not going to go down, I can be confident that, okay, fine, this works. Now roll out this new feature. So in this framework, we normally have two set of users to identify the particular risk associated with getting this new feature into the platform, and in which we, in a randomized way, put one user group and expose them to an older website, and another user group and expose them to the new features, right, or the new website. And when we compare the results of a particular metric, like the number of clicks or the number of purchases and so on, we should be able to see that these two groups are either exactly the same or quite different. And if it is on the negative side of the difference, we say the feature is not good. And even if when the difference is not at all there, we say even if we bring this new feature, nothing is going to happen. So this A/B testing framework is quite robust in its own way, right? And a very common question, if you have like worked as data analyst, or if you are expecting to be like sitting for this data analyst kind of a role, knowing A/B testing framework is very important. Okay, so sometimes also when you do these kind of A/B testing sort of analysis, people normally come out with sort of saying what should be the sample size of my users whom I should be getting to participate in my A/B testing framework. Or also when you are building some models, you might see that there are certain statistical measures which has to be evaluated by the end of model building exercise. Like if you're building a machine learning model, let's say, and you want to see if those metrics on which I'm evaluating are really good or not, right? So in that, sensitivity is one of those methods or like metrics which we normally evaluate. And I'm going to show you something that we normally refer by the name confusion matrix. So I'll spend some time explaining this and then come to what do we mean by like sensitivity. So let's say you are building a model, right? A model for predicting whether a particular customer is going to purchase from my platform within 1 month or not. Right? So very simple problem statement, which might include many variables that we would bring in, and then finally build this model saying, okay, this is my final model which says with 90% accuracy whether my customer is going to buy from my platform, let's say an online e-commerce platform, within next month or not. So this is my model. So now, without going into the details of the model, let's assume that after you build the model, you have got the results. So while we analyze and evaluate what the result is all about, we might come out with a confusion matrix. So what it says, so obviously when you are building a model which follows a supervised way of learning, you will see from the historical data, after people have purchased in the platform within next 1 month, whether they are buying or not. So I can obviously create a really good training data set, right, which will contain the information after people let's do the first transaction with me in next 1 month, whether they are buying the next product or not. So with that data set, I train my model, and the way confusion matrix puts that is by saying my actual data says something and you have predicted something, right? So let's kind of get into the details of that. So this particular box which says my actual data says the customer will buy, and you are also predicting the same. So this we call the true positive. The prediction is actually true, right, in a positive direction, saying the purchase happened. Now like move or diagonally opposite to this TP, which is this TN, which is true negative, which means the prediction of your model saying the customer will not buy is actually matching with the actual data as well, right? So both of these values, the true positive and the true negatives for the two cases, is the right predictions from your model. But consider the off diagonal elements, the false negative and the false positive. And these two cases, this is sort of an error. Why? Because your actual data says the customer is not going to buy in this case, let's say, but your prediction says he is going to buy. So the prediction is actually positive, whereas the actual data is on the negative side. So this is a false prediction, right? So you have your, in this case, your FP, which is the false positive cases. And on the off diagonal element, if you look at this one, which is Fn, which is your false negative, for the cases where you are predicting the customer is not going to buy. But in the actual data, it says that customer actually has bought the product. So in this case, the model is wrong. So the type 1 and type 2 errors needs to be taken care of when you are building any machine learning model. If these errors are low, then your model is going to move towards that 100% accuracy mark. But normally any machine learning model has its own limitations. So particularly, there is one metric which we refer by calling sensitivity. So what happens is these true positives and true negatives needs to be controlled, right? If my model is very good in true positive ones, like the positive cases of when the customer is buying, but it is doing very bad job when the customer is not buying, the cases in which the customer is not buying, then the model has some sort of issues, right? It is doing only good in one place, but doing very bad on the other case. So I need to find out that by some metric. So sensitivity help us to find that out, which is in simple terms is a ratio between the true positive. In the denominator, we have all the cases of positive predictions. So imagine now if the type 1 error is going to grow, my sensitivity is going to come down. So if my true positives are like very high, the sensitivity will also be high. So this is sort of what we call the statistical power. If this sensitivity is really good, I would say that my positive cases are predicted well. And the exact opposite of this sensitivity is what we know by specificity. So we need to make sure that in a very good machine learning model, sensitivity and specificity both are balanced, right? So in very simple terms, this is what will be like mean here, the ratio of true positive by the total positive events there. And as I mentioned, both of these sensitivity and specificity play a good role when you want to evaluate a model's output, right? And one more common problem. So these questions might be immediately following one another. When people ask you about sensitivity and specificity, as you know, it's about the machine learning model's output, right? When the model is done, you understand whether the model is good or not. So in those cases, we also come across some kind of issues like overfitting and underfitting given machine learning model, right? So these words are very common. And the idea is, depending on the complexity of your model, you might see that you want to adapt very sort of exactly to your data points, or you might want to do a generalization. So for instance here, if I have these red and blue dots here, right? And if I draw a curve like this, which separates the red from the blue, and when this separation happens, I am building actually a classifier using some sort of modeling technique. But now imagine by drawing a smooth curve like the one which is given in black, you might be overgeneralizing it, right? By which I mean there might be some red dots on the other side of this boundary. You can obviously see that. But the moment I am kind of a bit more flexible by drawing this green boundary, which actually covers all that issues which is coming out with these red dots on the other side of the boundary. So this green boundary has like taken care of that. But the problem, when we are building any model, right, the idea is you need to generalize to the pattern found in the data. So if you don't do that generalization well, you are underfitting. But if you do that generalization like too specific, you are overfitting. So this curve might be represented by some polynomial, right? But that zigzag kind of a polynomial might be a bit more complex than a smooth curve like the one which is shown in the black. So you need to be very careful when you are building a model, particularly in the cases of regression models, where it is represented by a line and a polynomial. You need to make sure that the polynomial is not so complex, at the same time not so simple. Then you will either end up in an overfitting situation versus an underfitting situation. So we need to have a good balance between these two, right? So in summary, when kind of statistical questions comes in, it would mostly covering things like some basic statistical properties, as you would be like very aware of, like things like standard deviation, averages, how to interpret median, how to interpret quartiles, right? The first quartile, second quartile, and so on. And what do you mean by percentiles, right? These are some basic questions. A bit more complex in nature might be discussions around sensitivity, overfitting, underfitting. These are like statistical ideas. So you want to prepare maybe from a basics level using the properties like standard deviation, mean, and so on, till things like overfitting, underfitting, statistical, the sensitivity and specificity kind of ideas. So that will like make your ground a bit more stronger when you are going for the interviews. And these are at least the bare minimum for you to understand in the statistical concepts, right? Even anything less than that, you might like face some difficulties in the interview. Okay, but let's also talk about now questions which are related a bit more on data analysis. So let's see what kind of data analysis questions which might pop up in the interview. Okay, so some generic questions like this. People normally do analysis on structured data, which is in rows and columns, but there might be cases when the data is not so well structured, and those places the data might be textual. For instance, in Twitter, right? If you're doing any sort of algorithms like sentiment analysis, quite commonly known algorithms. So in that case, the sentiment analysis could be for a brand, for a election campaign, or maybe something else around your product features and so on. So text analytics in its own are really large domain, and in Python as well as R, there are number of libraries. So in particular, R has libraries like TM, right? The text mining package. Python as well, we have packages like pandas, packages like the NumPy ones, right? And also packages like NLTK, which is built only for natural language processing. So it can deal with many different sort of text mining approaches or text analytics approaches. So in comparison, if you talk about, as I said, the robustness in Python is much more than in R, but in terms of features, both are powerful enough with the libraries and packages that it offers, right? One of the fundamental sort of starting place when you do any analysis. So when you are given a data set and you are asked to do some sort of basic analysis of what that data tells you, maybe typically of questions like, I am in a retail business and my sales in a particular region is going down. So this is an analysis that is expected out of you, and you need to dig through in understanding what really is the problem in the sales going down. So if this is sort of the data which is given to you, you might want to first look at the transactional data which is present in the system. Then you might also want to go to data outside of your network. Maybe you might get the sentiments of your customers from social media platforms and so on. So there will be different sources of data that you will collect. But oftentimes collecting the data is not only the task, right? And not like only building a model or doing statistical analysis might like come very later in the stage. But what comes before that, after you have collected the data, is to make sure that the integrity of the data is maintained. You get rid of all the unwanted noise from the data, and then finally prepare the data for doing the sort of modeling exercise or doing descriptive analytics on top of it. So this cleaning and understanding the data, doing a lot of explorations with plot, in essence takes close to 70 to 80% of your time in any data analysis task. So if your company maintains the data in a very well structured way, this kind of heavy time which we spend on data analysis might be reduced, or the data cleaning might be reduced. Otherwise, you need to like take this up for any new project that you take up, which the data is not available in a prior, or you don't have like any pipeline which do this cleaning. You have to write it down of your own. So very, very important. If you don't do the cleaning part and understanding the data well, the analysis or the models that you build might end up giving you a very, very bad performance, right? So very important. As I said, 80% of the time people normally spend on this task, right? And oftentimes when you are analyzing things like the example I told, my sales are going down, what do I do? It is not possible to come out with such answers to complex problems like this with just one variable, right? So you might also want sometimes to move beyond one variable and talk about, let's say, how to do multivariate or bivariate kind of analysis. So oftentimes this question comes up, where you like asked to distinguish between this univariate, bivariate, and multivariate analysis. And the idea is very simple. In any sort of analysis, it is not only one variable which kind of decides the end output of your analysis, but there are multiple factors involved. So when there are multiple factors involved, you might also want to look at things like correlation. There are multiple variables. You want to see if there is any correlation between these things. Sales are going down, but because of what? Is it because my sales representatives are not going to the market, or is it my products are bad, or is there some other reasons? So with all the variables in one place, you might want to go and dig deeper to see if there is any relationships coming in the variables or not. And when we collectively get all these variables together and do some sort of coherent analysis around the problem, you come out with a really crisp answers to what you are trying to analyze, right? And moving on, there is also times when people do some sort of grouping, right, with the data. You do a sampling, right? You get a data set in your system or in whichever servers you are doing the analysis. But in that, there might be many number of times when even the randomized sampling of getting the true representative from the population like that might not work well, right? So in those cases, you might want to do some sort of systematic sampling, or maybe a cluster based sampling as well, wherein you might decide to say, I want to analyze the issue with only 5 regions in my mind, and with the 5 regions I'm going to form different clusters. Or in the systematic sampling, you might also want to say that with the 5 regions that I have got, I might want to analyze only for one product, right, which is not doing that good in the sales. So these kind of sampling techniques, like the cluster based one or the systematic sampling techniques, and there are different names for this, people might be able to give a very good interpretation of what really went wrong in whichever sort of analysis you're doing. So one example is like sales going down, but you can adapt this to other analysis as well. But the idea is instead of doing a randomized sampling by which we are not very sure which kind of data is coming in the data set which we want to use for analysis, but if we do it in a cluster basis, a cluster or a systematic sampling, you know exactly which clusters or which sort of regions in this example you are like analyzing, and in your end of the analysis you'll be very able to say this is not like a randomized sample that I have taken, but from these 5 regions. So there are many different ways of doing clustering, cluster or sort of the systematic sampling, which kind of helps in this particular final end results of your analysis, to put your end results in the right perspectives, right, instead of doing a randomized sampling. Okay, one more quite a useful sort of an idea, kind of widely borrowed from the field of linear algebra, and this is a bit related to what we earlier saw between moving from one variable to multiple variables, right? And eigenvalue and eigenvectors, kind of a concept borrowed from linear algebra, helps us to bring in some way a linear combination of different variables together. For instance, in some complex analysis, it might happen so that given a data set, it might have many columns, right? Let's assume you have a data set with 1 million rows, and let's assume 10,000 columns. So, and these 10,000 columns are some features. There are complex problems like that. But in most often, like most of the time, not all the 10,000 variables are useful, right? The input variables. So what we can do is, we might want to transform this data set in a lower dimensional space, by which we mean this 10,000 columns can be reduced to, let's say, only 100 columns, right? So eigenvalue and eigenvectors are these ideas which helps us in this transformation. And the idea is, can this 100 variables be represented as some sort of linear combinations of the 10,000 variables? And if I'm able to do that, my dimensionality is reduced, the time I take to do the analysis is kind of also reduced, and the representability which will come with only 100 variables will go up, right? So quite a powerful idea, eigenvalues and the eigenvectors. And as I said, the eigenvectors is kind of that linear combinations of many kind of variables there. And this calculations around eigenvectors normally happens for a correlation or a covariance kind of a matrix, which, as you know, the measure correlation is also about how two variables are related, or how strongly two variables are correlated. right? So that's why we are also saying this eigenvectors can help us to compress the sort of data that we have, right? And that's because of one eigenvector can be representing 100 column, 100 variables together, right? So that's sort of how it works. Quite a powerful idea, and commonly used methods for reducing the dimensions of a large data set, like the PCA, principal component analysis, is actually based on eigenvalue and eigenvectors. So if somebody asks you about eigenvalue and eigenvectors in an interview, also talk about the PCA, principal component analysis, which is actually based on these two concepts. So that gives them a good idea to the interview. Led, you know about eigenvalues and eigenvectors, and you are also able to think of its application, like in PCA, right? So we talked about this false positive and the false negative cases in our confusion matrix example. So this is exactly the same. We also talked about the type 1 and type 2 error. Okay. So, but let's now also drill further and say examples or kind of scenarios when the false positives are important and scenarios where the false negatives are sort of important. And by the term importance, we mean, are we like allowed to do this mistake? If we are building a machine learning model, are we even allowed to do a mistake on either of the cases, the positive or the negatives? So for instance here, if I take an example in a medical domain, where we have, let's say, a process called chemotherapy, which is normally given to cancer patients, which is a radioactive kind of a therapy which kills the cancerous cells, right? So it is very focused sort of a therapy on the cancerous cells. So what will happen if you like predict, let's say you're building a model for detecting cancers, right, given a CT image, and this model would obviously not be 100% correct. All machine learning model has its limitations, but you are here required to predict this, whether a patient has cancer or not, and based on that, radiologist might decide that whether the chemotherapy is right for this patient or not. But imagine now, if you have predicted somebody to be positive for cancer, but the patient is actually not having the cancer cells there, right? So in those cases, you might end up saying, let's go ahead with the chemotherapy, but the side effects of chemotherapy are like very, very adverse, right? Because you're giving these therapies on the healthy cells if the patient is not having the cancers. So in these cases, sort of the false positives becomes a bit more important. So it will be absolutely fine if your model says the patient doesn't have cancer, even if there is like this slight possibility of cancer present in the cells of the patients. But in that case, you are not like exposing the patient with a chemotherapy there, right? Which is like more harmful than saying that the patient doesn't have the cancer, right? So in these cases, the false negative, though the false negative itself is not so good in this case, but at least with this particular example, the false positive gets the importance than the false negative. But both are bad, as you know, right, from the confusion matrix discussions. So in simple terms, it is better to not expose the patient with a false positive with a treatment like this, chemotherapy like treatment, then it is like much better than saying you don't have cancer. Okay. And a very similar example in some other context might also come up. So if you would like to think of some other examples in the same context. Okay. So where is the other case now, which is the false negative, right? So we talked about the false positives importance, but there might be also cases where false negative might become a bit more important there. And for examples like this, if you are, let's say, building a model where you want to convict a particular criminal basis all the records and the arguments which has happened in the code, right? And let's see what would happen if you make a criminal go free, right? Because your model says it's false negative. Though the person is actually a criminal, but because your model predicted based on all the evidences you had, the person is not a criminal, so you are letting a criminal like walk free in society. So that kind of is more harmful than convicting that person, and maybe for a prolonged period you might also want to get more evidences and build a stronger case. So it is fine to keep a suspect in behind the bars for a longer period than letting the suspect go free there when we like know that it might be a case of a criminal going free from the judicial systems there, right? So in these cases, the other case becomes more important. So keep in mind, it is very easy to get yourself confused between this false negative and false positive. But if you keep an example in mind always, and like don't give any room for confusion there, though it is a confusion matrix based on which these two ideas comes in. You will be able at every time put these examples in front and talk from that. So if you start to explain what false negative is in terms of the formula, you might get confused. But if you take an example and then explain, things are much more clear for you as well as the person who is hearing that in the interview. Right. And in cases when both are important, typically the one which relates to banking industry, you are building a model which will decide whether to give a loan to a person or not, basis many of the input attributes that around which you have like collected the application from the customer. But here you say if the customer is really good and you are missing the opportunity there of not giving the loan versus the customer is really bad in terms of his or her credit history and you are giving the loan. In both the cases, in one case you are losing the business, in the other cases you are taking a risk in which you will lose your money, right? So in this case, in this example, both kind of has an equal role. So if your positive or false negatives are in either of this is high, you will end up losing some chunk of your money there. Keep these three examples in mind, and every time you get to like hear false positive, false negatives, things should not be like confusing at all. Okay. So now let's also talk about building a machine learning model. So far we have discussed about what happens after building the model, right? But let's get one step back and see how do we normally build a machine learning model and what kind of processes we normally follow. So when we are like building a machine learning model, we know that we need to, given a data set, we need to divide it into different buckets or different parts. So the commonly known divisions that we like have is your training data, right? Then we also divide the data into something called test data. And sometimes people also divide or keep one portion of your large data set, which is called the validation data. So oftentimes people confuse between the test data and the validation data, right? So what happens is in the training process, there are certain models wherein while you are training, you will use the training data obviously, but in the process of training, you can also involve something like a validation step, right? Which will make sure that during the process, there is one part dedicatedly given for the validation of the model. And when the model is done, you might see that the final model is well trained on the data, at the same time validated. But when the model is completely done, then only you get into a process that we call testing, right? So you can imagine like this. You have a data of 1,000 records. You keep some 700 records for training, 100 records for validation, and the remaining 200 records for testing. So there are three splits, right? If I would like to explain this with an example, this is how it will happen. So there is a process called k-fold cross-validation, in which k can be any number like between 5 and 10. Mostly there are like standards saying 5-fold cross-validation or 10-fold cross-validation. And the idea is when you are building your model, you will work with a training set, right, and a validation set, in which a small portion of the data you keep for validation and the rest you use for training. So what you see here, test set, can be like replaced with a validation set, right? And you can see that this is a rolling sort of subset, and you keep changing it in each fold. So you go for the first fold of the iteration, you keep one validation set, and the rest of it is the training set. And the next fold, you move this window to another subset, and the rest is training data, and so on. And when this model is done using this k-fold cross-validation approach, in the end you will get a model which you can then use on the testing data to see if the accuracies are good or not. So this kind of brings in a lot of performance improvements. People have also found validation set to be a really good way of tuning the parameters. In many machine learning models, as you might know, there are something called parameters, typically in the neural network models. And these parameters need to be tuned as the model is kind of proceeding. So we cannot use the testing data set for tuning these parameters. So validation set kind of comes very handy in those cases. Right? So we just talked about the cross validation. So when you keep moving this validation set in each of the fold, first fold, second fold, third fold, and the validation set is keep changing, you kind of do this process of cross validation, right? And the idea behind doing cross validation is to see how well is your final model generalizes to the data that you have. So independent of which data you use for training, your model should generalize. Because oftentimes it happens when you train your machine learning model, it works very good in the training part, but when it comes to the testing, the model does very bad. The same problem with the overfitting and the underfitting cases. So in this approach of cross-validation, you have made sure that your model has trained on various subsets of the data, right? And in the process, we also have this small validation set so that every stage of the cross-validation process, you are able to use a different subset. So that means you have trained your model very well. So irrespective of which data you use, your model is going to do well in the testing cases. So that's how cross-validation brings in the capabilities. Okay, so with the two pillars like the statistical analysis and the basic data analysis, I hope you are getting some sense of how people ask a particular question coming from either the model building perspective or from normal data analysis perspective, right? So we're going to now go a bit more deeper into questions which might relate directly to machine learning. So these are all the most questions that you have seen so far are either saying how do we do analysis after the model is built, or how do we normally perform simple data analysis like A/B testing frameworks and so on. But what if you are asked something very particularly from a machine learning domain, right? So the next set of questions will cover those part. Like people might also start with the basics like what do you mean by machine learning? So the idea I think must be very clear. You are given a set of data points particular to a given domain, right? And you would like to build a learning algorithm which will take the historical data and predict something for the future. So as we talked about in many examples, finding whether a convict is actually convict or not, like predicting if given the evidences if person is a convict there or not, or predicting whether we should be giving a loan to a customer or not, right? Predicting the onset of cancer in a given patient's by using the given patient's historical records and so on. And now this algorithms are now even becoming more complex, like it is starting to work on speech data, face data, which are mostly used for biometric authentication systems, right? So many use cases coming up from various industries, right? So in machine learning, the most commonly used two types of learning, the supervised and the unsupervised learning. There are like two other types as well, the semi-supervised and the reinforcement learning. And the idea is around if you are given a set of input attributes, do you have a label which can help to learn the input attributes around any data points that you have, or you don't have, right? So if you have, then the approach could be a supervised learning approach, versus if you don't have, then the approach is more an unsupervised. So some examples of the algorithms are like support vector machine, regression, naive-Bayes, decision trees. All of these are the supervised learning algorithms. So in a very simple terms, if I say you are given an input attributes for identifying, let's assume a sort of given an image of different fruits based on the characteristics of the fruit, can you like identify whether it is apples, bananas, or the oranges? So if I'm given that label with me, the model will run keeping in mind that given these characteristics, this is an apple, this is an orange, and this is a banana. But in the other case, if you go for a clustering approach where such a label of saying that it is an apple, banana, and orange is not available, then we might just simply segregate the data points with the input features, maybe with color, with texture, or with the shape, right? With that, we can maybe say that particular fruit with this shape is like into a bucket which we can like call banana, or another kind of a spherical shape, it might be apple or an orange. So depending on the presence of a label, we can say either to use supervised or an unsupervised learning. And both of these approaches are quite common. And sometimes there are certain algorithms which can have the both ways. It can also learn in an unsupervised manner and the supervised manner. So depending on how you model the problem. But the fundamental difference comes from the fact on whether we have the label or not. Okay. So when we talk about the supervised learning algorithms, other name for supervised, kind of one of the types in the supervised learning algorithms is classification, right? And the classification is around given a set of input attributes, and the label is like categories, right? For instance, if it is fruit, bananas, apple, and oranges, like if it is a customer whom we want to predict into either kind of a defaulter type or a good customer. So the classes are two, like one which is saying the customer is going to be a defaulter, the other says the customer is going to be a good customer. Same is true for when you want to build a classification algorithm for detecting cancer, whether the patient has a cancer or not has a cancer, right? Or if you want to detect, let's say, a malicious content or a malicious file, which might be a virus, Trojan, or worm or something else, right? So in that case, the classes are now many. So more than one class can also be there. But the fundamental idea is we are following a supervised learning algorithm, but the type of problem we are solving is a classification problem. So instead of saying classification algorithm, we can also say it's a classification problem using a supervised learning algorithm. So these are the various types of classification algorithms, like the linear regression, decision tree, then you have the support vector machines, and so on. Right. So now let's talk about one of the types of classification algorithm called the logistic regression. Right. So very commonly used algorithms, and banks or companies as big as like American Express sort of have leveraged the logistic regression algorithms to quite a extent, and they have like built a really robust implementations of these algorithms, particularly in banking sector. Cases like predicting whether a customer is going to be a defaulter or not, given if I issue the customer a credit card or give a loan. Right, these kind of decisions can very robustly be taken from a logistic regression algorithm. And these algorithms are best suited for two class problems or a binary problem, right? Where you have either yes or no. Quite a common technique, as I mentioned, and in all the possible cases, wherever you have these binary classes of problems, you might use a logistic regression. A political leader winning a election or not, somebody getting a success in an examination or not, and as I mentioned, whether to give a loan to a customer basis, whether he or she is going to become a defaulter or not, and many of these like binary types. So keep in mind, logistic regression works best for classification problems with two class. So one of another widely used algorithms like the recommender systems. And like I think this particular algorithm doesn't need introduction, so this is that common nowadays. Take an example in Amazon. You have a product which you are browsing, the products which comes in bottom of the widget which says you may also like, or customers who brought this also brought this, right? So these sort of recommendations is actually from a recommender system which is running in the backend. If you like take YouTube example, if you watch one video, the next videos like starts to come one after the other. Right? That again is a recommender system working in behind the scene. Or if you take Netflix, if you watch a particular movie, it starts to adapt, right, to a movie which you might like. Netflix also uses recommender systems. The applications are like coming more and more as sophisticated systems are building in, right? Facebook uses it for recommending friends. Right? You have a set of friends, and based on your data coming from the contact mail list, Facebook starts to curate friend suggestions, right? And all of these are algorithms which might benefit the business in some way or the other. For Amazon, it is if you give a recommendation below a page, people might buy more than one product in a transaction. For Facebook, they will grow their network of people, right? Their connection between the users are going to go stronger, and hence obviously the kind of ads that Facebook wants to sell will also starts to grow, right? And more the users, more the connections, more is the sort of interactions you know about the connections, as well as the behaviors that people show in a social network. So the fundamental idea behind all these recommender systems is to get a meaningful comparison between two users or between two items. Right? For Amazon, between any two products, what's the similarity? If the similarity is really high, recommend that product to the for a given product in consideration. Or if you find that two users are very similar in, let's say, Facebook, you might want to show to each other that you have another friend whom you might want to connect. Right? So there are like many such use cases which comes out the moment you get into the deeper understanding of recommender system. But the fundamental idea is, how do I compare two items? The items might be product, people, movies, and so on. And how do I compare two users in simple terms? So this is what a recommendation system works on. So there are quite famous examples like the collaborative filtering approaches, user-based collaborative filtering algorithms, or the item-based collaborative filtering algorithms. Both of the algorithms are quite commonly used in recommender systems. And nowadays people have also moved on to latent factor-based models like the SVD, singular value decompositions, and many others. So we talked about classification problem, and then we said logistic regression is a binary class problem, right? So you might also be asked something around linear regressions. So what if I don't want to have a class of a particular user or a patient or something like that, right? But instead, if I would ask you, can you give me a crisp value instead of a class? Right, so when I'm like classifying a given file into good, bad, in which bad can be virus, worms, trojans, these are the classes. But if I don't want class, but rather, for example, if I want to know the exact value of a house in a particular locality in my city, how do I calculate that? Right, so linear regression models in machine learning is one such technique which can regress over a given input data, which might include the properties of the houses, like number of bedrooms, the area in square feet, and so on, and finally predict a value, a crisp value, which will be exactly in terms of, let's say, dollar or in any other currency, the value of the price. And the idea is, once again, that you have a training data with you which has labels. So from the past data, I know that given these attributes of the house, what should be the ideal price of a house? I'll use that as my training data and then build my model for future. So now with any such similar pattern in any data which is going to be coming in future for maybe a new property which is built in some XYZ location, I can use the model and predict exactly, because these features are somewhere similar in that locality, the prices might be in a particular range. So a model like linear regression will learn those patterns in the given input attributes and try to predict the price of the house. Right? And the idea is, if I have a set of data points, I want to build a very generic model like drawing this line, which is as close as to all the points, right? So you can like draw infinitely many number of points if you are given a set of data points like this in a two-dimensional space. But the one which is the shortest or the closest to the points is the best line. So the red line which you see here is like far away from all these points, right? So this is not a best line. But if I see this blue line, which is very close to all the data points, is like one of the best lines which I can get from these points, right? So the idea here is to fit a line passing through as closely as possible to all the data points that I have and minimize the so-called the error, which is nothing but the sum of all the distances. Right, so there are simple linear regression ideas, and the fundamental idea that we are following here is your variables are having a linear relationship, which means with the increase of one variable, the other also increases. But if you have a pattern which is not so linear in shape, like if you are like not able to draw a generic line, but the representation or the sort of points are aligned in a way that you can only create a model which is polynomial. So in that case, linear regression will not be so useful because the relationship is not linear anymore, right? So in that case, you might want to go for some other regression approach, maybe like a polynomial regression, which has a non-linear relationship between the independent attributes. So quite a common approach, and it has like a really large chunk of its explanation coming from the statistical ideas. Statistical ideas like hypothesis testing, p-values, confidence intervals, and so on. So if somebody is asking you around linear regression, better would be to start with saying how you build a linear regression model, right? And then you might give some examples of it. So at best, if you're not comfortable with these ideas like p-value or hypothesis testings, you might want to refresh that before you like go for any interview, because if linear regression comes up, these concepts needs to be a bit more explained. Right. So when I talked about the recommendation algorithm, I mentioned something about collaborative filters, right? The user-based collaborative filtering or the item-based collaborative filtering. So these are the two commonly used sort of recommendation algorithms, right? Normally referred to as item-based, so IBCF and the UBCF. And the idea, as I mentioned, is to compare to users or to compare to movies, or let's say items in particular. So the item can be anything, a product, a movie, or a person. And the sort of way it builds the model is given a lot of users and their particular, let's say in this example, their rating to a movie, we now need to find out, can we recommend for some users based on the behaviors of other users or their ratings to the movie, some suitable movies or not. So for example, here for Carol has not seen the movie 21, right? So there is a question mark there. So can I predict this value? If it comes to be, let's say, like close to 2, I won't recommend the movie. But if it comes to, let's say, somewhere 3, 4, or 5, yep, the model says, yes, recommend this movie to Carol. Okay. So one more fundamental problems on when you build the models. So as I mentioned in the earlier discussions, that when we are doing some analysis with the data, after you collect the data, there requires a lot of cleaning, right? And exploration as well. So in that process of cleaning and exploring the data sets, you might often find there are some extreme points. So for instance, if I'm building a regression model for predicting the house prices, and there is this one house which somebody has sort of able to sell for a very high price by means of maybe some auction or some other sort of marketing gimmick there, the point might mislead the model to predict or get itself towards that outlier point, right? So we don't want to like move towards an outlier point, but we need to deal it separately. So if you don't have a better explanation for why that outlier is in terms of an input attribute, better is to remove it. So for instance, if I'm like analyzing any data in an e-commerce world where I'm going through all the products and the sales that the product has seen in last 1 week, and on the last 1 week there was a particular day when a kind of a sales day was there. Like nowadays e-commerce companies do this a lot, but in those sales days you would obviously expect that the product's purchase is going to go very high, right? But does that mean that it's an outlier? To me, not, because if I'm able to explain an outlier by saying that this was a discount day, I might be able to handle it separately. Either I can like simply take all those points which are for the discounts day or sales day and keep it separately, or if I would like to have the variable like saying whether the given day is a sales day and keep the outlier as well, then the analysis goes in a different direction. So it's important you handle the outlier before you start to build your model or do any analysis. Otherwise your insights or your model's output might totally give you a different direction. And there are very different ways to handle the outliers. So some people use approaches like removing any data points which is like outside of the range of mean plus 3 standard deviation, right? Or sometimes people also use the percentile way of doing it. Any point which is greater than the 99th percentile can be like removed. So these are like you are removing the toppers from the data points of yours of, let's say, a SAT examination or a CAT examination. So the outliers are sometimes can cause certain issues in explaining the model. So you can obviously imagine this in very intuitive terms also. If you have a set of scores for candidates who appeared for an examination, and there was one outlier candidate who scored really, really high. So do you have a way of explaining that outlier? You might be simply calling that person a talented person, but does that like explain the model? Maybe difficult, right? So better is to keep those exceptional cases separate and do the analysis with the rest of it. So which gives you the good pattern or good insight from a data. So that's how you like normally handle an outlier, right? And this quite often is an important question to answer, that if you are given an analytics project with a lot of data, how do you normally approach it, right? In typical cases, the first step is to really go deep dive into the problem in hand. And the problem needs to be defined very crisply. So never define a problem which is broad in sense. So for example, if you are building a model for customer segmentation using a clustering approach, so instead of saying build a customer segmentation model for all the categories of products, that can be like a broad problem. But if I say build a customer segmentation model only for fashion category of products, right, then the problem becomes crisp. So defining a problem statement and its understanding is the foremost task. And then comes the kind of exercise of exploring the data, in which you will identify outliers, missing values, and if you need any transformations like converting from a log format to a wide format or the vice versa, you do all that steps in the second and the third step. And once we have found out that the data is very good now, after we have removed all the outliers and the missing values and so on, you then start to understand certain relationship, like given input attributes relate in some way or the other, right? So this is a stage where you start to prepare for any further insight building exercise or like model building exercise. And let's say if you build the model in this step, the immediate step is to validate it, right? Whether the model is really good or not by using a testing data, right? And once, let's say, all of these is done and you are either coming out with a insight or a model, you would like to see in long term how this model is going to perform. So it might happen so because every model is not static. Your data is growing on daily basis. So if you want to build a really robust model on a growing times, it should append, the model should update based on the new data which is available, right? So over a period of time, you should track and analyze how good the model is performing on a real world data. And if the performance is going down, then it's time to retrain the model and maybe come out with an updated model on the data that you are already given, right? Okay. So one more task, as I was explaining in the cleaning process, how do we treat the missing values? So there are quite a number of techniques to do that. So for instance, if you have an attribute, let's say age, right? And you are analyzing this age in various segment of people, people who are teenagers, people who are professionals, people who are still in their college and so on, right? And there is one value missing in one of these categories of people, let's say teenagers. So if the age is missing, because I know I am analyzing a group of people who are teenagers, by looking at the average age in the teenage group, right, I can maybe impute a value. So instead of discarding the entire row because I don't have the value of age, I might be able to impute it by some simple measures like this, calculating the average in that group and putting the value there, which will not be completely wrong because I know there is a very strong evidence teenagers would be more or less in the range of let's say 16 to 20, right? Even if I'm wrong in my average calculation, it might not be so high. It might be like just plus or minus 1 or 2 years. So which I'm like fine with if I want to keep my data retained. And you might see that in your many applications, sometimes having a kind of discarding a particular row because of missing values might be very costly because the data is limited in number. So that's why people normally do this at a sort of mean, minimum or maximum kind of a value, or they also calculate the average and impute the value there. So there can be some other pattern-based imputation also possible, but I'll just give you an example. And in other cases, if nothing is possible, by putting a value, if everything is going to be misleading, then better is to like remove that. But that can only be done if you have a surplus of data with you. If not, then be cautious of removing any values, particularly the missing ones. Okay, so this question particularly pertains to a machine learning algorithm called k-means, right? Every time you run the algorithm, you have to define what should be the value of k, right? So there are approaches like elbow curve, which plots the kind of a scatter plot between the x-axis, which is the number of clusters, versus y-axis, which is the WSS or within sum of square, which is also known by the name distortion. The idea is, when we are building the k-means clustering algorithm, if we find at one point, if you like keep increasing the value of k, at one point we find that the distortion is low, which means the distance between the data points within a cluster is as close as possible, and the distances between two cluster points, like a point in cluster 1 and a point in cluster 2, is as far as possible. So if that's the case, then the distortion will be like very low. But if your points inside a cluster itself is very spread out, and your clusters are very close to each other, then the distortion is going to be very high. So in those cases, the value of k needs to be maybe further increased. And at one point, using an idea called an elbow curve, which will show you a small kink from where there is a sharp dip in the distortion values, and that is an appropriate value for k while we are building a k-means algorithm. So this is how it looks like. So you can see here, the x-axis is the number of clusters and your y-axis is your within group of sums of square. And at one point you can see there is a sharp dip here, and after this point, which is like circled in red, the value sort of almost saturates. So this maybe I can use as the appropriate value of k. So value of k can be like 6 in this case. So I hope you are now getting comfortable with questions around data analysis, statistics, and even the machine learning part. So the next pillar, which might very closely be associated with statistics as well, is around probability, right? So it is like sometimes in most of the standard literature, probability and statistics comes together. It is not inseparable anytime. So in the naive-Bayes algorithm, like this is one of the machine learning algorithm which is based on the Bayes theorem. Probability ideas are quite a lot used, and there are some really niche probability concepts like the probability graph models, which is actually based on the basics coming from Bayes theorem and the fundamental properties around probability. We'll not go to that detail of probability in interview questions. If you have an expertise around probability and probability graph models or naive-Bayes kind of algorithms, feel like confident to speak about it. but most of the time the probability questions are quite basics and fundamentals, like the one at least which is asked in interviews, depending on obviously in which place you are giving the interview at. So let's also like see some sort of approach in attacking probability problems. Okay, so I'll like read it out for you what the problem is here. So it says in any 15-minute interval, there is a 20% probability that you will see a shooting star, like a good example rather. So what is the probability that you see at least one shooting star in a period of an hour? So there is unknown information given to us that every 15-minute interval there is this 20% probability you will see at least one star. So we now want to calculate this probability in a period of 1 hour, right? So what is the sort of approach we would take here? So let's build this systematically. So we know one fact, that probability of not seeing the shooting star in every 15-minute interval is 20%, which like comes down to 0.2 in probability terms. 20% chances or 0.2 probability. And as you know, probability is always between 0 and 1. So if I would like to calculate what is the probability of not seeing the shooting star in 15 minutes, which is like the opposite of this, right? If I take from, so these are like independent events, right? So if I take 1 minus of the probability of seeing one shooting star, 0.8 will then become the probability of not seeing the shooting star in 15 minutes interval. Okay, what I need to do is then probability of not seeing this shooting star in another 1 hour, because these are now independent events, like seeing a shooting star in first 15-minute interval, the second and third and the fourth in an hour's period is independent of each other. We can multiply this probability like this. So 0.8 into 0.8 into 0.8 into 0.8, which comes down to a value of 0.4. So the probability of not seeing the shooting star in a period of 1 hour is 0.4, right? And if we know the value of this probability here, all we like have to do to get the value which we are interested in is, which is the probability of seeing the shooting star, is 1 minus the probability of not seeing it, right? So the probability here comes down to 0.5. Quite a simple approach in terms of how it works, right? So there might be like similar tricky ways of putting the same questions, but if you know one approach and having the idea of independent event is, right, you may be able to get the understanding or like formulation in this way. And also keep in mind, given a sort of a sample space and many events from the sample space, the sum of the probabilities cannot exceed 1, right? So that's why we are able to do this. If I'm saying tossing a coin, the probability of tail is going to be 0.5, and the probability of head is going to be the other event, which is going to be 1 minus the probability of tail, right? So similar is the case with here as well. We are like treating this as a binary problem. So depending on which problem you are going to tackle, the approaches are going to be the same, but the language and sort of the trickiness in the question might increase, right? So this is how you can attack that. Okay, so there is this one more question, which is around generating a random number between 1 to 7 with only a die. Okay, so let's also think about this, how we can like approach this problem. So we have like seen how we generate random numbers from a given set of points, but this kind of says that we want to do this with a die, right? By rolling a die, we want to find out a random number between 1 to 7. So obviously we know that the die has numbers between 1 to 6. So the probability of getting any one digit in the die is 1 by 6. Like if I do 1, 2, 3, 1 divided by the total number of possibilities, that is 1 by 6. So that will be my probability of choosing any one of the digits there. But it is saying we want to generate this random number between 1 to 7. So where do we get the 7? So obviously the requirement is that we can like roll the dice twice, right? Then the number of possibilities increases. So as I said, there is no way we can get the 7th one, right? Because we have only 6 digits. But if you roll the die twice, the number of possibilities of generating this 7 random numbers increases. So in this case, we have now 36 different outcomes possible. You can like do the maths there, which is nothing but 6 cross 6. So 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and for the rest of the digits the same way, right? 6 cross 6. So that's the different number of outcomes we can get. So now for us to get this 7 sort of random numbers, and imagine that this idea actually relates to a sampling technique as well, when we say we want to get the numbers between 1 to 7, all of those numbers should be equally likely, right? Otherwise it will happen that I might get 1 and maybe quite a number of times versus one particular digit like 2 only once or so on. But if I want to do a very good randomized selection, I need to be making sure the probability of picking any one digit between 1 to 7 is equally likely. If I'm not doing that, I might have a bias, right? So we have these 36 different outcomes. So how do we now make sure that this is like kind of equally likely? So first we have to like find out a number which is divisible by 7, which is close to 36. So maybe we can exclude one of the possibilities from the 36 combinations we have and keep only these 35 possible outcomes. So like excluding maybe 6, 6. This possibility if we remove, we are left with the remaining 35 possible outcomes. So with this one reduction in the possible outcome, all we are left out with is all the possible combinations starting from 1, 1 till 6, 5, right? Now if we divide this into 7 parts where each like contains 5 possible outcomes. So what will happen is with the 7 parts, each having 5 outcomes, whenever any one outcome comes in these 7 parts, I'm going to assign a value to it. So for instance, if I assign the first 5, because we are going to divide it into 7 parts, where each part will contain 5 possible outcomes. So maybe the first 5 outcomes I will assign to the part 1. So whenever that 5 outcomes comes up, I will say the random number which I have generated is 1. In the second part, I will keep the next 5 outcomes, and whenever that 5 outcomes comes in rolling these 2 dice, I will assign that a value 2, and so on. So this way, what we have done is we have made sure that the random number that we are picking between 1 and 7 are equally likely. If you don't do that, then there will be a bias. So you see here how sort of statistics is like merged with probability. That this is how the two ideas and subjects travel together. Okay. So one more question on the same line. So for instance here, if you have a couple and let's say they have 2 children. So at least one of which is a girl. So this is a given scenario. So the question asks you what is the probability that they have 2 girls, right? It becomes a bit more like tossing 2 coins problem, right? Where there are different combinations. So what you can see here is a couple has 2 children, so at least one of which is a girl. So we have a known fact with us. So now all we need to do to kind of calculate this probability is to generate all the possible combinations. The first child being boy, the second child being girl, the first being girl, the second being boy, and so on, right? If you write that down, this is what the possible combinations are. And all these 4 are equally likely, as you could see. So with this case, we have like in the question, at least one of the children is a girl. So that means only 3 combinations are left out with us. The combination where both the children were boys is excluded. So in a very simple manner, you can like just go ahead and calculate the probability of having 2 girl childs will be 1 by 3. So there are total 3 possibilities which comes in the denominator, and you have like the probability to choose. So there is only one event which favors this probability, like saying 2 girls out of the 3 that we have. So 1 by 3. So let's take up this question here, which says the jar has 1000 coins, of which there are like 999 coins which are fair, right? Which means the head, and there is one head and one tail. And there is one coin which is like tampered with, and both the sides of that coin is head. We need to now pick a coin at random from this jar and toss it 10 times, right? So given that we have seen then 10 heads already in that 10 times of tossing the coin, what is the probability that the next toss of the coin is also going to be head? Right? We are given a statement here that 10 heads are already seen. What is the probability that the 11th toss would be a head? Okay, so let's see how we approach this. So let's first put these 2 possibilities in place. There is this 999 fair coins and one doubly headed coin, right? Double headed coin. So we need to see the probability of how many times we can get that double headed coin. So if I look at from the jar's perspective, choosing a fair coin from this jar is 999 times out of all the 1000 possible coins, so which comes to be 0.9, so high probability. But for the unfair one, though there is a small probability, but it might also appear some point, right? So the probability of selecting 10 heads in a row would then be either you would get a fair coin and toss 10 heads continuously. So this is one possibility. The second possibility is to select an unfair coin where the possibility of head is like 100% because there are both the sides of the coin is head. So the probability of selecting 10 heads in a row would be the selecting fair coin multiplied by probability of selecting 10 heads, which is nothing but each coin which you are picking up is independent of each other. Getting a head there is also independent there. So the probability is 0.5. That's why we are able to multiply it. So you have here the probability of picking a fair coin to be 0.9 and multiply that with 0.5 10 times. And that's your like probability which you get after that. So this probability of A is selecting a fair coin and getting 10 heads. And the probability of B is selecting an unfair coin, and we know whenever we select that, the surety is we always get a head. So then the probability of B becomes 0.001. So now what we need to find out is this probability where we can sort of say, given we have these two cases, what is the probability that we are able to come out with the 11th head, right? So how are we going to do that is by selecting this kind of combining this probabilities into a sort of form like this, where we are calculating, given these two possible cases, what is the sort of likelihood of with a fair coin getting 10 heads and with an unfair coin getting that one head, right? So those two are the probabilities written here, 0.49 and 0.50. So finally, with these two probabilities known to us, the probability of selecting one more head would mean that in the fair coin the probability is 0.5, right? So which you already know. And in the unfair coin the probability is always going to be 1 because we have both the sides as head. And both of these probabilities we are just going to multiply with the probability of the fact that already 10 coins have been seen and its head, right? So that's what we are like multiplying in front of it. So if you put this into one formulation, you will finally get the probability of selecting another head is 0.75. So which is like slightly more if you didn't had this sort of one double-headed coin. If that coin would not have been present, the probability would be a bit more less here because all the coins are then fair. Okay. So thanks a lot for listening to this session. Hope this helps for you to prepare for your interviews. So reiterating the fact, give a very good emphasis on basic ideas from stats and probability. Also spend some amount of time understanding machine learning models and basic ways of doing data analysis and things like A/B framework testing and so on. So these are some broad concepts you need to know. Also spend some time on linear algebra kind of ideas like the eigenvalues and eigenvectors. It might also be helpful on certain questions. So all the very best for your interview, and hope you all get a really successful career in data science. Thank you.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!